illustration of what Parkinson's is and how you can take care of it. So right here I have the basal ganglia, to help you remember it. And this is dopamine. So dopamine is what is lacking, and usually there's also a inverse relationship with acetylcholine, but that's the main concept that you should understand in what Parkinson's is and the pathophysiology of what's keeping the go, no go, or keeping the go signals from coming to the cortex, right? As talked about before, the thalamus was supposed to be letting the go signals get there, and the basal ganglia right here, is the trouble area. And so here's dopamine. So the lack of dopamine is what's getting to the basal ganglia is the main problem. So in clinical use, there's the Levadopa, which you'll notice is dopa. It's very similar in structure. The nitrogen's here, and there's carboxylic acid. So the catechol ring, being similar to dopamine, allows for high affinity to the same receptors, and is critical for the transport and to be converted easily to dopamine by decarboxylation. So the catechol ring, right? The 6 carbon ring with 2 adjacent alcohols, very similar. So to this point, and there's the amino group. The amino group, which differs, is needed for the recognition by the AADC, so the amino acid decarboxylase, and to cross the blood-brain barrier. This is a big concept. So now we're going more into the organic chemistry in the pharmacology of how we can treat, as far as we know, Parkinson's disease, and it's probably an emphasis I'll be on more in the future. So thirdly, there's which I notice is different from the dopamine to levodopa, is the alpha carboxyl, so the carboxylic acid right here. You can notice there's a difference between the dopamine and levodopa, right here. And it's for the amino acid like transport and the crossing the blood-brain barrier. So getting through the door is the main part, because once you have crossed or not crossed the blood barrier, dopamine cannot cross. This is like the main problem of dealing with Parkinson's, is that dopamine isn't easy to get to the basal gang, right? The basal gang has all the dopamine being broken down before it gets to here. And levodopa is the main solution we have so far to that. It's the gold standard. Then here we have carbidopa, which also looks very similar. It inhibits the conversion of L-dopa to dopamine, but in the area that it's not crossed the blood-brain barrier yet, because it's crucial to remember that L-dopa has changed. Once it has changed, it cannot cross. So this keeps it from being broken down before it gets to the brain area. But also, there's reoccurring problems with dopamine being broken down once it's there, because also when it is in the brain, there is more enzymes that want to break it down. So selegiline and rasigline are used to keep the enzymes from bringing down the dopamine, breaking it down before it's actually being used. And thirdly, so the first case would be levodopa is the closest thing to dopamine that we have that can cross into the brain. Carbidopa and entacapone. So carbidopa and entacapone are what allow the. I'll put a body here. That's. Let's put a body. Sure, the body. That sounds funny. So think of the body, Arnold Schwarzenegger here. The There is a lack of dopamine in the basal gang, right? So our main solution is to get levodopa into the body, which can travel up to the brain and be used there. But the first problem is that there are enzymes in the body that would break it down before, right? That would break it down before it's used at all into the brain. So it needs to cross the blood-brain barrier. There's the barrier. Carbidopa and entacapone act as enforcers for levodopa to get inside the brain. But also when you're there are two more enzymes that would also like to break it down. So the enforcers for that would be silicoline, razagoline, and tolcapone, which you would see here. And for silicoline and razagoline, you would see the malreactive propyl amine groups, which would be the triple bonds you see, and these keep the levodopa from being broken down in the brain before it's actually used in the basal ganglia as it's needed. And then thirdly, which I don't have here, there's the issue of Parkinson's being a progressive disease and neurons dying that would produce dopamine. So there are also many other pharmacology solutions to that, but that's a deeper issue. But the main thing you should remember is that dopamine is trying to get to the gang. The gang is the basal gang, is the core of what allows the thalamus to reach signals out here, right? So, so what should be able to come here through the thalamus, being uninhibited, is not working. It's no go. It's not going. It's staying here, and you ideally want to get dopamine here, so you can have more control of your body. Am I right? So the best solution we have as a gold standard for today is levodopa, because it gets still, be committed to the body, and make its path there. And the enforcers are carbidopa and entacapone, which would stop the enzymes from breaking down levodopa before it gets here. And secondly, when you're here in the area, there's still two more enzymes that would like to break it down before its use of the gang to the gang. And thirdly, there's the issue of the neurons being broken down that produce dopamine, and there are many other solutions to that, but that's the main idea that I wanted to bring today. And the functional groups, right, that differ from levodopa and dopamine are not an accident, because they allow for a crossing of the blood-brain barrier, right? And yeah, that's it for today. Thanks.